All right, good morning. Welcome back to Calc 1, everybody. I appreciate y'all being here. I found something, so I was talking with my Calc 2 students yesterday about something called an improper integral. And you guys, we haven't talked about that, so don't worry. But there was a concept there that was useful for them that I realized, boy, I really wish my students knew this back in Calc 1 so they could like have it in their brain kind of festering that whole time as they get ready to talk about improper integrals and why some transformations are so special. So I wanted to share something with you. So instead of kind of jumping right into our normal lecture, today's going to be a little bit different. We are, of course, going to have a normal lecture, but I want to begin by showing you something on the internet. Sorry, that's my email. You don't need that. Here we go. Good old internet. Where to begin? So let's begin here. 3 Blue 1 Brown is one of the best math YouTube channels I've found. And you can imagine being a nerd growing up on the internet and loving mathematics. It's just one of those things you do. You watch math videos. Um, this guy is amazing. My dog just farted as he ran away. This guy is amazing. Really, really, really good. And if I were taking Calc 1 right now, I would be so grateful that this series of videos, sequence of videos, exists. So I want to encourage you guys, I'm going to paste the link in the chat here. I want to encourage you guys to take a look at a couple things. First, so there's the Essence of Calculus videos. I think this might just be the first video. I don't remember if this is the link to the actual playlist, but you guys are all plenty savvy to find your way to the playlist from there. The other thing, the thing that I was really wishing my Calc 2 students had a prior understanding of was a way of thinking about derivatives and functions that mathematicians use all the fucking time. See, graphs are great. We love graphs. Graphs are wonderful because they can tell you kind of everything that you want to know about a function all at once. It's a single picture that encodes all the data. But the visual intuition that comes from looking at functions as graphs is different than the visual intuition that comes from thinking about functions as transformations. And in actual fact, most functions cannot be thought of as graphs because most functions don't have a one-dimensional input and a one-dimensional output. Most of the functions that I study have two-dimensional inputs and two-dimensional outputs, which would make their graphs four-dimensional and very, very hard to draw or see. So instead, we think of them as transformations. And this is the key. So it's really about the first 10, 15 minutes of this video that I would love my Calc 2 students to have internalized. The whole video is very good. I invite you to check out the whole thing. But the first 10 to 15, well, it's not even a 15-minute, 16-minute video. First like 5 minutes video. Scaling factors is so both of these are 3 Blue 1 Brown videos. They're both really excellent. I'll show you a few seconds of this one.
Anything like my first introduction to calculus, or any of the first courses that I've seen in the years since, there's one topic that you will not see, but which I believe stands to greatly accelerate your learning. You see, almost all of the visual intuitions from that first year are based on graphs. The derivative is the slope of a graph, the integral is a certain area under that graph. But as you generalize calculus beyond functions whose inputs and outputs are simply numbers, it's not always possible to graph the function that you're analyzing. There's all sorts of different ways that you'd be visualizing these things. So if all your intuitions for the fundamental ideas, like derivatives, are rooted too rigidly in graphs, it can make for a very tall and largely unnecessary conceptual hurdle between you and the more quote-unquote advanced topics like multivariable calculus and complex analysis, differential geometry. Now, what I want to share with you is a way to think about derivatives, which I'll refer to as the transformational view, that generalizes more seamlessly into some of those more general contexts where calculus comes up. And then we'll use this alternate, of course, scope idea.
Check this out. This is really
The
good.
basic idea behind the alternate.
The thing that's new here that I want you to think about is this.
Function as mapping all of the input points on the number line to their corresponding outputs on a different number line. In this context, what the derivative gives you is a measure of how much the input space gets stretched or squished in various regions. That is, if you were to zoom in around a specific input and take a look at some evenly spaced points around it, the derivative of the function of that input is going to tell you how spread out or contracted those points become after the mapping. Here, a specific example helps. Take the function x squared. It maps 1 to 1, and 2 to 4, 3 to 9, and so on. And you could also see how it acts on all of the points in between. And if you were to zoom in on a little cluster of points around the input 1, and then see where they land around the relevant output, which for this function also happens to be 1, you'd notice that they tend to get stretched out. In fact, it roughly looks like stretching out by a factor of 2. And the closer you zoom in, the more this local behavior looks just like multiplying by a factor of 2. This is what it means for the derivative of x squared at the input x equals 1 to be 2. It's what that fact looks like in the context of transformation.
This is the same as the slope of the tangent line.
Points around the input 3,
but it's just a different way of thinking about it.
Stretched out by a factor of 6.
All right, that's enough of that. So I really encourage you guys to take a look at those videos. I think that they will help you develop a good intuition, a powerful intuition around what calculus functions, derivatives are. And I know for sure when we talk about integration via U substitution and specifically doing U substitution in certain improper integrals in Calc 2, that is a concept that will be useful to refer back to. So yeah, that is all. Just wanted to share that with you guys. All right, back to your regular scheduled programming. This is MAC2311, section 002. Today is 2/24/21. It's a lecture. I'll tell you that. Today, so we've talked about linear approximation, differentials, and meaningful amount. I wouldn't, let me see actually, so where is your syllabus? There's a little bit of a challenge coming up here. So exam 2 is ideally coming before spring break. It was unclear at the start of the semester what was going to happen with spring break because UF canceled theirs, but we didn't. But we talked about doing whatever UF was going to do. And then UF started late in order to, make up for canceling spring break, but we didn't start late. So I don't, Santa Fe is going to have a spring break. I would be shocked if they were to, within the next week or two, say, oh, no, spring break is canceled. So in order to make sure we are ready for all of the things that we need to have for exam 2, I think it would behoove us to do one of two things, either move exam 2 to after spring break, or move a few topics from exam 2 to exam 3. If we move a few topics from exam 2 to exam 3, that's going to make exam 3 a heavy exam. It's going to have lots and lots of stuff on it. So right now I'm leaning towards moving this to after spring break. But remind me, so because my other Calc 1 class is in a slightly different place right now. We got to talk about 3.10, right? Linear approximation and differentials, the linearization function. And certainly we've talked about related rates, but did we get a good treatment of section 3.10? Did you guys feel like you've seen enough problems from this section where we were like approximating square roots? Okay, so I won't go back and spend more time there. Just making sure I'm not shorting you guys out on stuff. Then I'd like to talk more about mins and maxes and kind of return to this graphing, specifically the graphs of f and f primes, see how those guys are related to each other. So 4.1, I think we got through Fermat's theorem, right? And we talked a little bit about finding critical numbers, but we haven't talked about the first derivative test yet, correct? First and second derivative tests, those are things that we have not discussed. So that means we're right here. We're right at 4.3. Okay. Applied optimization is a tough section. L'Hopital's rule probably will do that on Friday. So curve sketching and applied optimization, those are going to have to wait until next week. And that would mean really rushing exam 2 if we're going to do that before the break. So here's what I'm going to do. I'm going to give you guys warning right now. I will be letting you guys vote on Friday, right? So today is Wednesday, our next class meeting on Friday. I will be letting you guys vote on what you want to do. We can have exam 2 next week. We can have exam 2 next Friday. It means I would be pushing the applied optimization section to exam 3, which is going to make exam 3 tougher. Let me describe to you a little bit why I think that might not be a bad idea. I think that might not be a bad idea because over spring break, you guys are going to do what anybody wants to do over spring break when they're in college and, you know, go to the beach, drink beer, whatever. Probably not a lot of mathematics. Even if I assigned you a project or something, I know that we're not going to spend the amount of time thinking about mathematics that we should in the week leading up to a test. So one of the options we're going to have here is to take this section, applied optimization, and bump it down here. And that would mean this Friday, after we finish talking about L'Hopital's rule, I would put out your study guide. And next Friday, which would be the 5th, we would have exam 2. And exam 2 would cover up through section 4.5, but would not cover section 4.7. Option.
How much is 4.7 different than like exam 3 sections?
Considerably different. Exam 3 sections, these are all about integration. And these don't really have much to do with derivatives at all. So if we were to put section 4.7 on exam 3, it would be kind of floating around out there as its own thing. It's a tough section and it has to do explicitly with and then the other thing here is to delay the exam until after. We would run through this more or less in the order it's in here. So I would talk about L'Hopital's rule this Friday, a little bit more about curve sketching and applied optimization the following week. And then I'd give you guys a little project here for the spring break. And then you would have your exam like right away after we come back from spring break, like Monday or Wednesday after we come back from spring break. So those are the two options. And please just keep them in mind. Think about them a little bit between now and our next class because I'll be letting you vote during our next class. It's up to you guys. So either we're going to have the exam before spring break and push 4.7 to exam 3, or we're going to have the exam after spring break containing all the normal material that would be on exam 3. That's section 3.4 up through 4.7. All right.
Project, what do you mean?
Oh, was there a question there, Robert?
Yeah, can you hear me?
Yeah, I can.
What do you, when you say project, what do you mean?
It would just be like something for you guys to work on over spring break that would kind of try to keep you thinking about mathematics. It wouldn't be grade heavy, but it would be just like some homework or I don't know. I don't have anything particular in mind. I just want to make sure that you guys would have something to do, so that we're not just forgetting all of our mathematics over the break.
That's a good question. Would it be a project and a study guide, or just all in one?
Separate things.
Okay.
Yeah, the project, like I said, would not be a grade intensive thing. It wouldn't be something that's weighted heavily. It would just be something that I could give you without feeling guilty that would get you to think about mathematics over the break.
Gotcha.
All right, so we want to be thinking not so much about the hypothetical projects, but thinking about how this will affect our exam scores, how well we're going to do on the test, given each of those options. All right, so let's come back here. I want to talk to you guys about graphs of the function and its derivative. So today we're going to talk about graphs of f and f prime, or how derivatives effect shape of the graph, which is section 4.3. So we know that y equals f primed of x is positive if f of x is increasing, and that f primed of x is negative when f of x is decreasing. Because if you look at the graph of f and you think about slopes of tangent lines, if I call this A, I call this B, and this is the original function f of x. If I look anywhere the function is increasing, the slope of the tangent must be positive. And anywhere the function is decreasing, the slope of the tangent must be negative. Positive tangent slope increasing, like here, 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 here. So f primed here is greater than 0. F primed here is less than 0. F primed here is less than 0. F primed here is still less than 0. F primed here greater than 0. Because f primed is the slope of the tangent line, if the original function f of x is going uphill, then the slope of the tangent line is going to be positive. And if the original function f of x is going downhill, then the slope of the tangent line will be negative. This leads to something called the first derivative test, but I think your textbook states it as a theorem, right? So the precise statement here, if f of x is increasing on the open interval I, then f primed of x is less than 0 for all x in I. Conversely, if f of x is decreasing on the open interval I, f primed of x is increasing. Sorry, this should be a, this is a positive, this one is negative for all x in I. Right, so it's just that same thing that we've observed in the past, that f prime is positive when f is increasing and f prime is negative when f is decreasing. Reformulated as a theorem, being a little bit more specific about where. So in the picture above, f primed of x would be negative on the interval negative infinity up, negative on the interval a to b. And that's precisely where f is decreasing. f prime of x would be positive on the interval negative infinity to a, union with the interval b to infinity. We can turn this around and say, okay, if I want to find where f is increasing or decreasing, I can find where f primed is positive and negative. So imagine I didn't know what the graph of f looked like, but I did know that f primed was negative everywhere on the open interval AB. Well, that would tell me that from A to B, f of x is decreasing. I wouldn't know anything more than that necessarily. I wouldn't know how fast it's decreasing or what the graph looks like, really, just that it's going downhill. But this information alone would tell me that f is going uphill from negative infinity to A, downhill from A to B, and then uphill again from B to infinity, which is enough to start getting an idea of what the graph of f of x looks like. And that's where we're going to go with this long term. So long term, what you should be thinking is, how can I take information from the derivative and use it to sketch the graph of f of x? So I know that I'm going uphill, then downhill, then uphill. That tells me the rough shape. It doesn't tell me where the graph is. Like, you could shift this whole picture up or down, and it would still satisfy these conditions. But it's enough to start giving me an idea of the shape. So your textbook phrases this. Here, 4.3. Right, increasing and decreasing. So if f prime is positive on an interval, then f is increasing. And if f prime is negative on that interval, then f is decreasing. In other words, this theorem that we have here goes both ways. So, yeah, first derivative test. There's nothing in between that? Okay, then we'll introduce curvature. So kind of the big take home here, if we want to find, if we have a differentiable function f of x and want to know where f is increasing and where f is decreasing, it suffices to find where f prime is greater than 0, where f of x is greater than 0. This will tell me where f is increasing. And where f prime of x is less than 0. This will tell me where f of x is decreasing. So we need to get good at solving inequalities. Right? If you want to know where a function is increasing, you need to take the derivative and then solve the inequality f prime of x is greater than 0. If you want to know where a function is decreasing, you need to take the derivative and solve the inequality f prime of x is less than 0. I'm going to do some examples with you, but before I do that, I want to refer you to something in the modules. So solving inequalities, I have a few things here. There's also one on solving rational inequalities explicitly, yeah, and solving polynomial inequalities. These things, so we can highlight here in the note. This module, or this part in the review material module, this part in the review material module, and this part in the review material module. These things are going to be very important to us. There's lots of good examples here that show you how to do it. Basically, what you're going to do is you're going to make a number line. You're going to break that number line up into regions, and then you're going to test a point from each region. There is something called a multiplicity trick, and I'll show you how to use that. But it's the same vibe for all of these. We end up making a number line, splitting the number line up into regions, and then figuring out whether the inequality is or is not satisfied in that region. Every single one of the same sort of things. All right. Not something else. Okay. So let's work an example. Let's see if we can't figure out, take a simple example. Extreme values. Let's find out where this function is increasing and decreasing. So 3x to the 4. I'll write this down and go back. Minus 4x cubed. Minus 12x squared. Plus 5. So find where f of x equals this is increasing and decreasing. Remember, answers to these sort of things are always open intervals of x values. That's something that we should learn in pre-calculus, right? When I ask you where is something happening, just like for mins and maxes, where is the max or where is the min? I'm asking what's the x value? And if I ask you what is the max or what is the min, I'm asking for the y value. So here when I ask where is this increasing, the answer should be an open interval of x values. Here's how we do it. We're going to take f prime. The derivative of this function here is 12x cubed minus 12x squared minus 24x. I'm going to find the critical numbers. Remember what a critical number is. Critical numbers are anywhere f prime is equal to 0 or f prime is undefined. We're going to take the derivative and find critical numbers. Critical numbers, remember, saying f prime of c is equal to 0 or f prime of c is undefined. They also have to be in the domain of the original, but here the domain is all real numbers because this is a polynomial. So I can factor out from this a 12x, and what will be left here is x squared minus x minus 2. And then I can factor this, x squared minus x minus 2. This is 12x times x minus 2 times x plus 1. So I calculate the derivative, factor as much as I can. If this were a more complicated expression for the derivative, I would want to like factor the top and the bottom. I would want to go through all the algebra procedures that you saw me doing on Monday to simplify. Remember that last example where we calculated critical numbers, right? It was quite a bit of algebra to simplify. From here, my critical numbers I can say. So f prime of x is equal to 0 if and only if, well, when is this equal to 0? X equals 0, x equals 2, x equals -1. F prime of x is never undefined. Because f prime is a polynomial, right? Polynomials are happy everywhere. So by calculating f prime and factoring it, I'm able to find where f prime is equal to 0. I just set each of these factors equal to 0 on their own. If there were a downstairs to f prime to anywhere the bottom was equal to 0, those would be places where f prime is undefined. So these are my critical numbers. So what I did here for Bruce, I just took the derivative using the power rule. And then to go from here to here, I factored out the GCF, the greatest common factor. Greatest common factor between 12x cubed, 12x squared, and 24x is 12x. So I'm able to pull that out. When I factor out the greatest common factor, that 12x, this is what's left over. 12x cubed divided by 12x is x squared. Negative 12x squared divided by 12x is just negative x. And negative 24x divided by 12x is negative 2. So that gets me to here. And now I realize, okay, I've got this thing all factored out. He's happy, but I still have this quadratic. So I'm going to factor this quadratic, and he factors like this. Once I have this is f prime fully factored. If I want to know where is f prime equal to 0, and remember that's what I want, I'm looking for critical numbers. You guys remember what critical numbers are, right? Critical numbers are anywhere f primed is equal to 0 or f primed is undefined. So once we have f primed nice and simplified, if I want to find my critical numbers, I just set f primed equal to 0. So I imagine setting this thing equal to 0. If I set this equal to 0, that means since it's all factored and stuff, I just have to set each factor equal to 0. This factor is equal to 0 when x is 0. This factor will make f prime 0 when x is 2. And this factor will make f prime 0 when x is negative 1. So these are my 3 critical numbers. If there is anywhere f prime is undefined, those would also be critical numbers, but f prime is never undefined because it's a polynomial. So we did talk about critical numbers, right? I'm just making sure again. I'm sorry, my brain gets a little bit jumbled because I do have a couple other Calc 1 classes and they're at different paces. Okay, thank you. All right. So now I have my critical numbers. The game is going to be to solve we want to solve the inequalities f primed of x is greater than 0 and f primed of x is less than 0, right? Because the solution to the first one will tell me where f of x is increasing. And the solution to the second one will tell me where f of x is decreasing. And that's what I'm after, right? Oh, shit. Yeah, we'll underline this. And so f of x increasing means f prime is positive. So if I find out where f prime is positive, that will tell me where f is increasing. F prime negative means f of x is decreasing. So if I find where f prime of x is less than 0, that will tell me where f of x is decreasing. So my goal is to solve those inequalities. The way we do that, we take the numbers that make f prime 0 and we plot them on the number line. So I'll plot negative 1 here, 0 here, and 2 here. The only thing that matters about the placement here is that their relative position is correct, right? So the gap size doesn't matter, it doesn't, but negative 1 needs to be to the left of 0, 0 needs to be to the left of 2, so on. The basic idea is if I want to find out where this function is positive and negative, I should find where it's able to change from being positive to being negative. In order to change from being positive to negative or vice versa, it has to go through the x-axis. It has to be equal to 0 or undefined. So these are the points where f prime is capable of changing from positive to negative or vice versa. So we chop the number line up into these intervals. So for example, between 0 and 2, f primed is either positive everywhere in there or negative everywhere in there. The only way f prime could go from being positive to negative is by passing through one of these 3 points. So between any 2 of them, f primed is either always positive or f primed is always negative. Does that make sense? This is something that is supposed to be discussed in pre-calculus, but I can't trust that it was discussed sufficiently well. So I'm taking a second to say it. The only way this function can go from being positive to negative is by passing through one of its roots. It's a polynomial. So between its roots, it's either positive or negative. It's not allowed to like cross over the x-axis without hitting the x-axis. These are the places where it hits the x-axis. So these are the only places where f prime can change sign. Alrighty. To the left of -1, f prime will either be positive or negative. If I plug in something like -2, so I'm going to test x equals -2. F primed of -2 is 12 times -2 times -2 minus 2 times -2 plus 1. I don't really care what the number is, but I know that this is negative, this is negative, and -2 plus 1, that's also negative. So each of these three factors is negative here. You multiply three negative things together, you're going to get a negative thing. F primed is negative everywhere from -infinity up to -1. What about between -1 and 0? There's a neat trick called the multiplicity trick that can help us here. The factor that gives the x equals -1 is this guy. He is a multiplicity 1 factor. Do you guys remember the term multiplicity from pre-calculus? Because he's an odd multiplicity factor, I know that I will change sign as I jump over -1. The other option here is to test something like -1/2. You can test something from each region. I'm going to get a little bit tired doing this, but if we test x equals -1/2, this factor will be negative, right? 12 times -1/2 is negative. This factor will be negative. -1/2 minus 2 is definitely negative. This factor will be positive. So in here we'll have negative, negative, positive, which means this is going to be positive overall. Between 0 and 2, we could test x equals 1. So what happens to f prime if I plug 1 in here? This would be positive, this would be negative, this would be positive. So I have positive times negative times positive. What is that overall?
Negative.
Good, yeah. I'll put them in down here. I'm not going to put the whole thing in, but f prime of -1/2 is greater than 0. F prime of 1 is less than 0. So this is a negative in here. And then if I test something to the right of 2, I could test x equals 3. If I plug 3 in here, this would be positive, this would be positive, and this would be positive. F primed of 3 is definitely greater than 0. So this is a plus. So what I've just done is I've built this number line for f prime. This tells me where f is increasing and where f is decreasing, because it tells me where f prime is positive and where f prime is negative.
Looking at that graph, I know you said that it can only pass through -1, 0, and 2. Does it always have to pass through it, or can it be like negative, negative, positive, negative? If that makes sense.
I think there's two questions in there. For a function to change sign, for a continuous function to change sign, it must pass through the x-axis, right? If you are continuous and you're going to go from negative to positive, that means you have to connect a point down here to a point up here. And the only way to do that is to go through the x-axis. Your other question is, is the pattern always like this? Does it always oscillate back and forth? The answer there is no. And this depends on something called the multiplicity trick, which I'll explain in just a second. So give me just one moment here and I will get to that. It basically comes down to the power of the factors here. You see how each of these factors has an exponent of 1. This is x to the 1, x minus 2 to the 1, and x plus 1 to the 1. Each of those is what's called a multiplicity 1 factor. If the multiplicity is odd, then you will change sign as you jump over that thing. So the multiplicity of x plus 1 here is odd, it's 1, which tells me that as I jump over this line, I will go from negative to positive. Or if I found this to be positive, I would go from positive to negative. But we'll come back and look at that a little more closely. The test points, the numbers that I test, have to be a number from each region. So the region over here is negative infinity up to negative 1. I have to take a point from inside in the interior of that region. So anything to the left of negative 1 would work as a test point here. Between negative 1 and 0, I have to find something from the interior of that region. Well, negative 1 is not in the interior, and neither is 0. Those are at the boundary. So it's something between them, negative 1/2 works. You could also use negative 1/9 or negative 0.7, whatever you want, as long as it's between these two guys. All right, so let's write down the conclusion. F primed of x is less than 0 on what intervals? On negative infinity to negative 1, unioned with 0 to 2, which means f of x is decreasing on negative infinity to negative 1, unioned with 0 to 2. And f primed of x is greater than 0, positive, on what intervals? Negative 1 to 0 and 2 to infinity. So f of x is increasing on precisely those intervals, negative 1 to 0, unioned with 2 to infinity. Now, there are faster ways to solve these inequalities. There are faster ways to come up with this number line besides test points. That's what I would like to show you guys, and I would like you guys to get good at, because it can save you boatloads of time. But before we do that, let me just verify the work that we did. So let's pop open a Desmos window here. My original function was f of x equals 3x to the 4 minus 4x cubed minus 12x squared plus 5. Here it is. All right. Here is the original function f of x. I can rescale my y-axis a little bit. Something like this, yeah? Okay, well, what do you see? From negative infinity to negative 1 and from 0 to 2, we're going downhill. And from 1 to 0 and from 2 to infinity, we're going uphill. Does everybody see that? Right. Everywhere to the left of the blue line, we're going downhill. And everywhere between the green and the purple, we're going downhill. That's from negative infinity to negative 1 and from 0 to 2. Remember, it's always x values. And from negative 1 to 0 and from 2 to infinity, we are going uphill. So this shit works. Right? That's precisely what we said. Decreasing from negative infinity to negative 1. Decreasing from negative infinity to negative 1 and from 0 to 2 and from 0 to 2. Increasing from negative 1 to 0, increasing from negative 1 to 0 and from 2 to infinity and from 2 to infinity. Yeah, that's a whole different matter. So how does Desmos know to graph this exact thing? Well, Desmos is just plugging in numbers, right? Desmos just takes this formula and plugs in a shitload of numbers all at once. And that's where it gets the graph. But if you want to know more about this, if you want to get the steepness correct, I will be showing you guys, that's section 4.5. Section 4.5 is how you can get really nice pictures just doing stuff like this, and we will get there. But before we get there, there's more to say. So first, are we comfy with this? Are we comfy with how we arrived at the answers to the question that was posed here? Right, decreasing here, increasing here. Are there any questions about how we got these answers? Okay. I'd like to draw your attention to something now, if I could. Let me come back here. I'm going to delete these. Let's just look in here. What kind of feature does the function f exhibit at -1? What's going on here?
It's becoming flat before it starts to increase.
That's sure, yeah.
Or it becomes a horizontal line.
So think about 4.1. Think about Monday's lecture. What is happening right here at this point? What would we call this point?
A local min or max, probably min in this case.
Yeah, this is a local min, right? It's the bottom of a valley. If you zoom in on this point and you look just at what's going on nearby, that looks like a min, right? Because the value of the function here is smaller than it is anywhere else nearby. This is a local min. This is a local max. This is a local min again. If you go from decreasing to increasing, that means you're going downhill, downhill, downhill. And then at this point, you turn around and start going uphill, uphill, uphill. If you go from downhill to uphill, that must be a local min. So here, we're going to make some notes. I'm going to redraw this number line on a fresh sheet here. I'll just redraw it down here. All right. This is our number line for f primed. And we were negative here, positive here, negative here, and positive here. So f is increasing. So f, we should say decreasing. F is increasing. F is decreasing. And f is increasing. So at -1, we go from decreasing to increasing. At 0, we go from increasing to decreasing. And at 2, we go from decreasing to increasing. If you're going from decreasing to increasing, you have to roll through a local min. It must be the case because you're going downhill, 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 and then uphill, uphill, uphill. That creates a valley. So this must be a local min. Now here I go from increasing to decreasing. If you're going up, 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 and then down, 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 that's got to be rolling over the top of a hill. This has to be a local max. And then here we go from decreasing to increasing again. I'm going downhill, 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 and then I'm going uphill, uphill, uphill. This has to be a local min. This is called the first derivative test. And if you look at the graph, it bears this out. This is a local min because we're going from decreasing to increasing. The only way to go from decreasing to increasing is if you roll through the bottom of a valley like that. So we have a local min at -1. Then over here at 0, we go from increasing to decreasing. The only way to go from increasing to decreasing is if you roll over the top of a hill like this. So that must be a local max. And then over here at 2, we go from decreasing to increasing. So this has to be a local min, and it is. This doesn't tell me anything about the absolute max or absolute min, but it does find me all of these local extrema, and that's cool. So this is a theorem called the first derivative test. This hints at the following theorem. And I want to say this the same way your textbook says it, so it's not confusing. We can add in some hypotheses here. We really should. What do I say? First, see a critical number for a continuous function. All right. Yeah, that's fine. If x equals c is a critical number for f and f of x is continuous at x equals c, then if f primed of x changes from negative to positive at x equals c, then f of x has a local min at x equals c. And if f prime of x changes from positive to negative at x equals c, then f of x has a local max at x equals c. And this, this right here is called the first derivative test. That's the sort of name for this theorem. So we're learning how to do a few things here. We're learning how to find where a function is increasing and decreasing, but we're also learning how to find local extrema. Remember in section 4.1, we talked about how to find critical numbers. And we said if f has a local min or local max at some point, then that x value at that point should be a critical number. Well, now we're saying if you know you have a critical number, and you know that your original function is continuous there, then by building this number line, you can not only find where f is increasing and decreasing, you can also find whether those critical numbers are minima or maxima or neither. It's all about this picture. It's all about this picture. So if you really understand this number line, then you're in good shape. You can answer where are the local mins and local maxes. You can also answer where is f increasing and decreasing in the same picture. Questions on this theorem? Okay, a little bit ago when I was showing that Desmos picture, Mackenzie asked a cool question. How does Desmos know how steep the curve should be or how steep the slope should be? The answer, unfortunately, there is that Desmos just does raw computation. It just finds all the y values on the graph by literally computing them, as at least many, many, many thousands of them. But we as human beings don't want to do that. We would get very, very tired. And there is a way to know more about the shape of the graph. It has to do with the second derivative. I'm going to take this away in just a few seconds. So if you're still writing or if you need a screenshot, now's a good time to grab one. Maybe I'll get some more coffee while you guys are writing. Okay. So I want you to think with me for a second here. We're going to talk about second derivative and concavity. Suppose this is the graph of f of x. Clearly, this function is decreasing everywhere, right? This guy is always going downhill. But if I pick a few points, let me come in here and pick a few points. And kind of just drawing the tangent lines. Of course, they all have negative slopes because the function is decreasing. But what do you notice about the slopes of the tangents themselves? How are they changing?
They're getting less steep.
Good. So f of x is decreasing implies f primed is less than 0. So all tangents have negative slope. But the tangent slopes are getting less steep. So let's try to graph f prime. Right, this is something you did on the first test. Given the graph of f of x, you try to draw a graph of f primed. I'm going to call this like 1, 2, 3, 4, and 5. And so down here, I'm going to do my best to sketch a little graph of f primed. Here's 1, 2, 3, 4, 5. I guess I should really, f prime, we know it's all going to be negative. Should really be going down here, f prime of x. All right. So based on this guy, I would say f primed of 1, that's really steep and really negative, right? So this is like negative 10. Based on this guy here, I would say f primed of 2, he's a lot less steep. I'll say like negative 2. And maybe f primed of 3, he's like negative 1. F primed of 4 is like maybe negative 1/2. And then f primed of 5 is like maybe negative 1/10. So here would be my graph of f prime. I'll mark this as like negative 10. So I'm like negative 2, negative 1. So f primed of 1 should be around negative 10. F primed of 2 should be around negative 2. F primed of 3 should be like negative 1. F primed of 4, well, it's like negative 1/2. We're getting up in here now, and F primed of 5 is like this. So the graph of F primed and this might not be perfect, but it should look something like this. What do you notice about F primed? It's negative, sure, but what else?
It's a reflection.
Oh, well, yeah, so it does kind of look like it might have some symmetry with F. But is F prime increasing, decreasing?
Increasing.
Yeah, F prime is increasing. Which would mean F double primed, the second derivative should be positive. This is how we learn about what's called concavity. The shape of the original function here is kind of like this, right? Kind of like a bowl, kind of opening towards the top rather than being like this. We call this concave up, and it corresponds to the second derivative being positive because the tangent lines are getting large. How do I say this? The tangent line slope is increasing. The slope of the tangent line as you go further out, this starts off very negative, then less negative, then less negative. So these are increasing derivatives. I'm estimating those, Fabrice. It's not a perfect thing. It's just an approximation, the same way that you guys were meant to approximate the slopes of the tangent lines on exam 1. I guess I should really use shaking equal signs here. These certainly are not exact. I'm just estimating. I'm just saying this looks like a really steep line with negative slope. So I'm going to say the slope is like negative 10. That's it. That's all the thought I'm putting into that. Not very much at all. But kind of the big idea is that to get this sort of bowl up shape like this, you need the slopes of the tangent lines to be increasing. And that means F primed is increasing. And that means F double prime is positive. So I'd like to describe to you now 4 different graph shapes, all the possible permutations of increasing, decreasing, concave up, concave down. So let me really quick finish up what we have here. We say that the graph of f of x above, like the one that's up here, is concave up. Corresponding with f primed increasing, or f double primed being positive. All right, and do you guys see the connection there? if any function is increasing, then its derivative should be positive. Here, f primed is increasing. So its derivative, which is f double primed, should be positive. That's the big idea, right? Since f primed is increasing, f double primed should be positive. F primed increasing is this graph shape where you're concave up in this kind of bowl shape here. It's really like this, right? That kind of bowl facing up shape corresponds to the second derivative being positive. And the way we get there is by thinking about the first derivative. The first derivative should be increasing, which means that its derivative, which is the second derivative, should be positive.
So for this graph, would f double primed of the would it just look like f of x?
F double prime would be positive and itself decreasing. Yeah, f double prime here would be similar in shape to the original. But that sort of oscillation thing is not the norm. That's not something you should expect in general. So let me show you these shapes and then I'll show you some more examples. And I think that'll help us start to get a feel for what to expect. You're getting at something very good there, Mackenzie, but I think you're a little bit ahead of where we are. So let's describe these graph shapes. According to signs of f prime and f prime prime, f double prime. So what are all the possible kind of combinations here? F prime can be positive and f prime prime can be positive. This guy would mean we're increasing, and this would mean we are concave up. Oh shit, come on, come back to me, camera. So if f prime and f double prime are positive, f prime being positive means we're increasing, f double prime being positive means we're concave up. What does this look like? This looks like this. This is the sort of graph shape there. This is the increasing concave up shape. We are increasing, and also the slopes of our tangent lines are getting steeper and steeper. So f prime is increasing as well, which means f double prime is positive. You could be increasing and have f double prime being negative, right? So this would be increasing and concave down. What does that look like? Well, you're increasing, but the slopes of your tangent lines are getting shallower and shallower. That's like this, like the square root function or the natural log function. This is increasing and concave down. We're going uphill the whole time, but we're slowly, our tangent lines are getting shallower and shallower. So f primed is decreasing. F is increasing, f primed is decreasing. And of course, you could have f prime be negative, right? And f prime prime could be positive. This would be increasing and concave up. So f prime is, sorry, f prime is negative. I'm so sorry, decreasing and concave up. Yeah, f prime is negative, so we're decreasing. F double prime is positive, so we're concave up. So decreasing, concave up, that's like what we saw here, right? Where f prime was negative, but f double prime was positive because f prime is increasing. So this shape looks like this. And then the combination that's missing here is decreasing concave down. So that means f prime is negative and f prime prime is negative. So we are decreasing and we are concave down. What does that look like? Well, that means we're going downhill and our tangent slopes are getting more and more aggressive, more and more negative. So that looks like this. This is called curvature. F double primed information, the concave up, concave down stuff is called curvature. And these are the kind of four graph shapes that we can more or less glue together to create any sort of shape we need. It's not super quantitative, it's very qualitative. But it will help you understand what's going on if you can detect whether or not a function is increasing, decreasing, concave up, concave down. And the sort of, again, the long game here is to get to a place where you can sketch a very nice graph by hand using this information from the derivatives and a few points, right? So you start off by thinking the way you would in college algebra or something, where you just find a few points on the graph, preferably like critical numbers or intercepts, that sort of shit. Then you find where your function is increasing and decreasing. You find where your function is concave up and concave down. The increasing, decreasing shit, we know that that comes from building a number line for f prime. Concave up, concave down shit, that's going to come from building a number line for f double primed. So again, in the long game here, we're going to be sketching graphs of f of x by first plotting some points, then building a number line for f prime to figure out where we're increasing and decreasing, then building a number line for f double prime to figure out where we're concave up and concave down. That will tell us what sort of graph shape we have in each of those little regions along our number line. And that will let us draw a really nice picture of the graph. Now, we're not quite there yet. We're going to get there. But before we get there, I just want practice coming up with these things. So let me see what we have from our textbook. It's our first derivative test. Oh, yeah, we need to talk about the second derivative test also. So what does f double prime say about f? This is the concave up, concave down stuff. So if f double prime is positive, then f is concave up. If f double prime is negative, then f is concave down. And you want to be able to look at each of these things and say what's going on here. So right here, we are increasing in concave down. And then at this point right here, we change to decreasing. There's an inflection. Oh, I should tell you what an inflection point is. Yeah. Okay. So definition. An inflection point on the graph y equals f of x is a point at which the concavity changes. All right, so either you go from f goes from concave down to concave up, or f goes from concave up to concave down. Inflection points tend to happen at critical numbers for f prime. Okay. Some weird ass noise outside my house. So an inflection point is a point where concavity changes. If we look in here, let's return to this example. Here I am decreasing concave up. Here I am increasing concave up. So everywhere in here, I'm concave up. But then you see over here, I'm concave down, right? This is increasing concave down. This is decreasing concave down. So somewhere between here and here, we change. Here I'm concave up. Here I'm concave down. So somewhere it looks like maybe right around here, there is an inflection point where the concavity changes. To the left of this point where my mouse is, the graph is concave up. To the right of this point where my mouse is, the graph is concave down. And then we stay concave down for quite a while until we get to somewhere right around here, maybe here. Over here, this is concave up, but over here, this is concave down. So there's an inflection point somewhere right around here where the concavity changes from concave down to concave up. And then it looks like we stay concave up forevermore. Let's see if we can find those. I'm going to return to this guy. Hold on to him. So let's return to this example. We know where the local mins and local maxes are. We know where we're increasing and where we're decreasing. We went through all of that. Let's see if we can find where this same function, f of x, which was 3x to the 4 minus 4x cubed minus 12x squared plus 5 is concave up and concave down, and then locate any inflection points. All right, so same example we were playing with before. If I want to know where the thing is concave up and concave down, I need to know f double primed. F prime we calculated before. That was 12x cubed minus 12x squared minus 24x. So f double primed, much easier to calculate from this form than from the factored form. 12 times 3 is 36. 36x squared. 12 times 2 here is minus 24x. And then minus 24. These are all divisible by 12. So I can factor out a 12. And what I get is 3x squared minus 2x minus 2, right? 36, 12 times 2. Yeah, all right. So if I want to find my inflection points, I want to know where f is concave up and concave down, that means I need to make a number line for f double prime. So I'm going to do the same thing here that I'd previously done with f primed. All this same shit. I'm just going to do it with f double prime now. So I need to factor this guy. Let's see. So 3 times -2, that's -6. Can I come up with two numbers that multiply to -6, but sum to -2? This might not be pretty. Well, it just has to be some like 1, 6, 3, and 2, right? None of those are going to sum to -2. Yeah, so we may end up needing the quadratic formula here. In the interest of saving time, Got, are these rational numbers? They're not, no. All right. So if we were to use the quadratic formula, we would find that f double primed of x is equal to 0 at x equals 1/3 minus the square root of 7 over 3, and x equals 1/3 plus the square root of 7 over 3. Let me just call this x0 and call this x1, so I don't have to keep writing them. Here is my number line for f double prime. X0 is 1/3 minus something, and x1 is 1/3 plus something. So x0 is definitely to the right, sorry, to the left of x1. And we know the graph of this thing is a quadratic function opening up because the lead coefficient is positive, which means that between its roots, it will be negative, and outside of its roots, it will be positive. So f double primed is positive from -infinity up to x0, which is this number, negative between x0 and x1, and positive to the right of x1. Let me add those to our picture here. So 1/3 minus square root 7 over 3. Let's do it like so. There's the point on the graph corresponding to this first root of f double primed. And the other one, it's going to look very similar. I just have to change the minuses to a plus. All right. So this example isn't super nice in that it, the numbers that we found for our inflection points are not really nice numbers, but you see what I'm talking about, right? We're concave up everywhere here. F double primed is positive everywhere here. And that corresponds to this shape, right? The shape kind of looks like it would hold water. This is concave up decreasing. This is concave up increasing. And then we turn here. Now we're concave down. Everywhere in here, this is concave down. This little bit is concave down increasing. This is concave down decreasing. And we stay like that until we get to this next inflection point. This is all concave down, and now here we change, and now we're all concave up. So those black points there are called inflection points. And inflection points are points where the concavity changes. We'll do one more example here. I'm going to let you look at this for a second while I let my cat in. Getting fights. I don't think we quite have time to work another example. I realize now that we've gone a few minutes over, so I appreciate you guys being patient and sticking around through this long. I hope you have a good idea of what it means for a function to be concave up or concave down. It's mostly a picture thing. If it looks like it would hold water, then it's concave up. And if it looks like water would run off of it, then it's concave down. And then we have those four sort of fundamental graph shapes corresponding to whether the first derivative is positive or negative, and whether the second derivative is positive or negative. Next time, we're going to talk about what's called the second derivative test. So how you can find local mins and maxes. The first way we have is that first derivative test we introduced today. There is another way that sometimes is a little bit quicker called the second derivative test. I'll show you that. And then we're going to move on to talking about L'Hopital's rule and indeterminate forms. So that is all I have for you guys today. Please do be working on the homework. There's quite a bit of it. Some of those problems do take a while. You need to find, increasing, decreasing, concave up, concave down, local mins, local max, and inflection points. But it's very much worth doing. If you get stuck on anything, you can visit me in office hours. If you have any questions, you can send me an email. Otherwise, I'll see you guys on Friday when we will be also voting, remember, to choose when we're going to have our second exam. That is it. Hope you guys have a good rest of your day.
That's really quick. Are you going to be posting the lecture for Monday?
It's already up. Yep, posted it.
Oh, okay, thank you.
Take care.